All right, axioms of probability and some properties. In this video, we're going to see some of the axioms of probability, how to compute probabilities for certain situations, and some examples. First, a probability is a function. In mathematics, the formal way to define a probability is by using the concept of function. Don't worry so much about it. Here, because of the nature of the class that is online, we won't focus so much on the mathematical background that we need or to understand this. I mean, the formal mathematical background. But you have to understand that the probability is a function with domain all the events in a sample space. And range the interval from 0 up to 1. And actually, this definition should be even more precise. But again, with this is enough. Now, so essentially we have probability is a function with domain, um, all the events in the sample space. Or well, remember that an event is a subset, so it's essentially all the subsets of the sample space. To the closed interval of real numbers from 0 up to 1. So this function, to say that we have a probability function, we need the function to satisfy certain properties or certain axioms. Remember, in mathematics or in general, well here, but to be more precise, here in mathematics, an axiom, this word axiom, is like a principle, something that you accept as truth, but without any proof of that. I mean, it's something that for many people we say that it's very obvious, and you accept it as truth without any demonstration. So first, the axioms that we're going to require for a probability function to be actually a probability function is this one. Axiom number one: the probability for any event should be greater or equal than 0. Axiom number two: the probability of the whole sample space should be equal to 1. And axiom number three: if I have infinite events, A1, A2, if I have an infinite collection of the joint events, by the joint I mean Disjoint means that the intersection for any two of them should be the empty set. I mean, they don't have anything in common. Nothing in common. So if they are disjoint, then the probability of the union of all of them is going to be equal to the sum of the probabilities. Yeah, I know. Here, maybe for some of you, you haven't seen something like this before, might be weird because here we're talking about the sum that is infinite. If you don't understand the notation by now, that's okay. We won't focus on it. I don't think so. We won't need it by now. So you need to understand only this is sum. We are adding. Let me write it here. This is like we add all the probabilities for the events. And this sum continues up to infinity because we are supposed to have an infinity amount of disjoint events. Yeah, again, maybe for you it's weird to know about an infinite sum. Again, I don't think that we're going to need this, and of course, if we need it later, I will let you know, and I will try to explain that in a precise way. But by now, it's okay. So we have three axioms to have a probability function. The probability for any event, this is probability of, this is, oh, all right. This, you have to read this as probability of the event A. Probability of A should be greater or equal than 0, not negative, never negative. The probability of the whole sample space remember this capital S is usually what we have for to denote the sample space. And axiom number 3, if we have a family of disjoint events, then if we want to compute the probability for the union of all of them, it's only if we add the corresponding probabilities. Probability of A1 plus probability of A2 and so on. Now, with these axioms, we accept as truth as something true these axioms, and then with this we can prove all the other properties for probabilities. For example, I'm going to give you one example for a proof. Yeah. So you can understand how one you accept some principles, then you can deduce the other ones. I mean, or the other properties or laws or formulas that we have. And essentially, mathematics is about that. So here, example. Prove that the probability of what? Remember, this is the empty set, so we have probability of the empty set. Probability of the empty set. The probability of the empty set is equal to 0. That's going to be true always when we have a function satisfying these three axioms. If we have a function like that, then the probability of the empty set is going to be 0. Proof. Notice Since we have the empty set, we know that the intersection of the empty set with itself is only the empty set, right? I mean, the intersection, the union, I'm sorry. The union of the empty set with the empty set is only the empty set. So if we compute the probability here, probability at both sides, because the empty set has nothing, is disjoint with the empty set, with itself, of course. I mean, they don't have anything in common. So the union, I mean, what I mean with this is that the empty set intersection with the empty set is the empty set. They don't have anything in common. So then the probability of the union, since I have a union, I can apply this formula, this property. At the probability of the union is going to be the sum of the corresponding probabilities. So in this case, it's going to be probability of the empty set plus probability of the empty set. And this is going to be equal to the empty set, right? Because of this. The union of the empty set with itself is the empty set. So this is equal to this. But I know that because of the axioms of the probability function, the axiom number 3, this one, then this is probability of the empty set plus probability of the empty set. Then this implies that we have probability of the empty set plus probability of the empty set equal to the probability of the empty set. And this implies that twice the probability of the empty set is equal to the probability of the empty set. And the only possibility for this is that the empty set is equal to 0. This implies that the probability of the empty set should be 0. And there you have it. So another property, the probability of the empty set is 0. More properties. The same, they can be proved by following the axioms of probability or the properties that you already know that they are true or you are proving or you already proved. Number 1, I'm going to write down this one as a property. I already proved this one. Probability of the empty set is 0. Number 2, probability of the complement for one event is 1 minus the probability of A. Do you think you can be able to prove this property by using the axioms? Number 3, probability of the difference, A minus B, or probability of A without B is equal to the probability of A minus the probability of intersection of AB. Number 4, probability of, probability number 4 is interesting. It says if you have one event inside other one that is a subset of other event, then the probability for the first one is no greater than the probability of the second one. I mean, if A is a subset of B or is a sub-event of B, then the probability of A cannot be greater than the probability of B. It's less or, in the worst case, equal. Number 5, for any event, the probability for any event always is between 0 and 1. This is an important property. For any event, here in this class, in this course, the probability in the way we specified it always is between 0 and 1. Always. That means if you have a probability greater than 1, speaking about real numbers, that is not possible. Not in this class, not in this course. And of course, if we have a probability less than 0, I mean beyond of 0, but to the left, it's impossible. I mean, we cannot have negative probabilities, not here. All the probabilities must be between 0 and 1 when we're talking about real numbers. Number 6, this is very useful. The probability of the union is equal to the probability of A plus the probability of B minus the probability of the intersection. Let me prove another one so you can see how this works. So I already proved that the probability of the antiset is equal to 0, but I'm going to prove now the property number 4. I think this is very interesting. If A is inside B, then the probability of A never is more or is less or equal than the probability of B. How can we prove this one? Yeah, a mathematical proof based on the axioms. So let me do it. Proof of the property number 4, this one. So the hypotheses are that A is a subset of B, and I have to verify that this is true. I mean, I have to prove this. But my hypothesis is that A is inside B. So I have since A is inside B, then I think you agree that the intersection of A with B is equal to A. You can draw a Venn diagram to intuitively verify that. If you have a set B, and inside it you have a set A, notice that what you have inside, the intersection is only the set A. What do A and B have in common? Only A. So always that happens always when you have a subset. The intersection of the subset with the set that contains that subset must be the subset always, right? So now notice that if all of this is part of the sample space, then the intersection of any event with the sample space is going to be the event. But another way to write this is for any event A, the sample space can be decomposed into any event A. In this case, the event A is representing an event and the union of the complement. One way to understand this is again with a Venn diagram. If I have the sample space A is S, and I have a subset or an event A, notice that what is inside, everything that is here in green is a complement. You see that? Everything that is in green is all of this is a complement. So if you compute the union of what is all the area in green with the circle A, that's going to be S. And that is true for an event. So it's true that S can be decomposed into the union of A with the complement of A, and this is true for any event. Now, you have to follow some properties for sets. Yeah, I didn't cover them, but I'm sorry, but we are not, by now I think we don't need them. But you can, one property for events, for sets is that if you have the intersection of B with a union, you can distribute B with the two sets as a union. This property is true. Then, remember that B intersection S is equal to B we have that the probability of B is equal to the probability of B intersection S equal to, notice, this B intersection S is the same as this. And not only that, this set with this set, they are disjoint, because here I have A and here I have the complement. By definition, A and the complement for any event A, they don't have anything in common. So this can be written as the probability, well, let me write like this: B intersection A union B intersection a complement. Or what it is saying, probability of B intersection A plus probability of B intersection a complement. Because, again, this set and this set, B intersection A and B intersection A complement, they are disjoint. So I can apply the axiom number 3. The probability of the union when they are disjoint is only the sum of the probabilities. This is what I did here. Now I have this equation, right? Probability of B is equal to probability of B intersection A plus probability of B intersection A complement. But all of these are positive numbers, or in the worst case, they are 0, right? Because of the axiom, probability for any event always is greater than 0. So this means that since this is positive, or since this is positive, 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 then this number cannot be greater than this, right? But what is this? Since A is inside B, A intersection B is only A. So I have probability of B is equal to probability of A plus probability of B intersection A complement. This is probability of A because of this hypothesis. So again, make this analysis. This positive number, or well, let's say that it's not 0, right? So if this were 0, then this has to be 0 too. But assuming that this is not 0, then probability of B is positive. Then these two numbers, again, or they are 0 or they are positive. If one of them is 0, then 0 is less frequent than positive. The theorem is true. But what about if the two are positive? If the two are positive, the sum of two positive numbers is equal to other positive number. But this one cannot be more than this, right? Because this is only like a piece for the whole probability of B. Then this implies the probability of A is no greater than the probability of B. And there you have it. This is true for any event A always that A is inside B. Probability of A is no greater than the probability of B. All right, so let's see examples more, not very abstract. All right, let's see first the most common way to assign probabilities. Let's say that we have a sample space that is finite with outcomes S1, S2, and so on up to Sn. If we have one event of S, then the way in which we assign probabilities, and with this is going to define a probability function satisfying the three axioms. Probability of A is number of elements in A divided by number of elements in S. Number of elements in A divided by the number of elements in S. This is the most common way, or at least when you are a beginner, this is the main way to assign probabilities. This reduces the cases to compute the problems to compute probabilities. They are reduced to what? To count. We have to count the number of elements in A and the number of elements in the sample space. That's why before we covered a little of counting techniques. So examples. For example, for the experiment, tossing a coin. We know that the sample space is head-tail. Let's say that we have the event observe head. Then A, since must be a subset of the sample space, has only one element, the one where we have head. And next I want to compute the probability for A. Probability of A is going to be what? Number of elements in A, in this case 1, divided by number of elements in the whole sample space, that is 2. And there you have the probability we observe. One way to model this is the probability to observe head when we toss a coin is 1/2. By the way, this is not the only way in which we can assign probabilities. I mean, of course, we're assuming here that we have to assume we're saying that the coin is fair. But well, we will talk about that later. But by now, this is one way to assign probabilities for this experiment or situation. Now, I want to point out, notice how 1/2 is a probability between 0 and 1. If you want to write this as a decimal, I mean 0.50, no problem, this is correct. If you want to express this as a percentage, no problem, it's going to be correct. How do you do that? Only multiply this number in decimals times 100. But when you do that, you will have to include the symbol for percentage. So 1/2, 0.50, or 50%, the three ways they are correct. Usually maybe you have seen or you have heard that the probabilities are expressed by percentages. I think that is the best way to communicate to the public in general. 50%. But remember that when you want to express it in this way, multiply times 100, you need to include the symbol for percentage. So I'm not saying that a probability is more than 1. No, it's between 0 and 1. But when you include percentage, the symbol for percentage, then yes, in that case, should be between 0 and 100%. But with common numbers, probability is only between 0 and 1. So don't forget that. Part B. Now imagine that we toss a coin twice. We saw that sample space before. The sample space when you toss a coin twice is head, tail, tail, head, 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 and tail, tail. We have 4 outcomes here. Now let's say that I want to compute the probability for the event observe exactly one head. So I have to consider for A, I have to count the outcomes that A has. In this case, are going to be only the ones where I see only one head. Head, tail, tail, head. And then the probability of A is going to be 2 outcomes divided by the total outcomes in the whole sample space. Then in this case, be careful. I have 1, 2, 3, and 4. So it's going to be 2 over 4. And if you want to simplify, is 1/2, or if you want, 50%. So we can say that when we toss a coin twice, what is the probability we observe exactly one head? Or one head is 50%. You see that? This kind of experiment, when you're tossing something that has only 2 outcomes and you repeat that several times, actually it has a general formula, but we will see that later. By now, other event here, for example, let's say that I define the event at least one head. At least one head means that we observe one head or more. So in this case, I have to take into account for B, the outcomes from S that they have one head or more. It's going to be this one, and this one. I don't have to include this one because this one doesn't have any head. So it's going to be head, tail, tail, head, and head, head. Then with this, what is the probability for B? Probability for B is going to be 3 out of 4, or what is the same in decimals, 0.65, or in percentage, 75%. So what can you say here? When you toss a coin twice, what is the probability that you observe at least one head? 75%. I think we have good chances, right? Now, you have to understand that even when I'm saying that this is this way, the most common way to assign probabilities, this one, of course, is not the only one. You can define actually any function on the sample space, and as long as it satisfies the 3 properties or the 3 axioms, then where are they? These axioms 1, 2, and 3, then all the properties for probability that we're talking about here, they are going to be true. But this is when we have to count. Sometimes we will have cases where it's going to be more like we have to focus on the area. For example, let's say that we have the circle or the circumference. On the Cartesian plane, let's say that we have this circumference with the center in the origin and with radius 1. So these points are 0, comma negative 1. This one is 1, 0. This one has to be 0, comma 1. And this one has to be negative 1, comma 0. So we know that the area for this, well, first, I'm sorry. Let's say that I want to compute what is the probability that if I throw a dart here, it falls in this region. Or other way to say this is, imagine that you're going to pick randomly one point, exactly one point in all of the circumference. What is the probability that you choose a point from the shaded region in yellow? How can you compute that? Well, we can again do a quotient in this case, but in this case we are not counting. We have to compute the area. So in this case, probability of A, let's say that this is A. Probability of A is going to be this area divided by the total area. So first, I think we can compute the total area, right? The total area is going to be pi times r squared. Yeah, remember the area for a circle is pi times r squared, but in this case, the radius is 1, so the area is going to be pi times 1 squared, and that is going to be pi only. Now, notice this area is 1/4 of the total area. So the area, the shaded area, is going to be only 1/4 times pi r squared, or what is the same, 1/4 times pi, or what is the same, 1/4 times pi divided by pi, and what it is 1/4. So what is the probability that if we choose randomly one point here, one point in the whole circle, the whole circumference, what is the probability that that point belongs to the shaded region A? 1/4. You see? There you go. All right. More examples. This one. Here we have to use the counting techniques we have learned before. It says you flip a fair coin 10 times. What is the probability that it lands on heads exactly 3 times? All right. Here first, this is going to be part A, and this one is going to be part B. First, I think we have to count in how many ways we can toss a coin 10 times. So for the part A, the probability of the part A is going to be equal, that's going to be the amount for which we're going to divide. I mean, we're going to divide by that amount. But notice, since we're tossing a coin 10 times, that means that let's say that these slots, they represent the 10 times we toss a coin here. So we can have, for example, one possibility, we have head, then tail, other head, and so on, maybe head, and maybe tail. And we have to take into account all the possible combinations. But notice that when we have 10 times this, for each, we have only two options. I mean, head or tail, two options, head or tail, two options, and so on, head or tail, two options. So this means that if we apply the multiplication principle, then this can be done how? Multiply 2 times 2 times 2 times 2, how many times? 2 raised to the 10. So here we have the number of elements in the sample space is going to be 2 raised to the 10. Now, what is the probability of exactly 3 heads? We have to take into account in how many ways we can choose 3 heads out of the 10, but that can be responded by using combinations. Combinations 10, choose 3. This represents ways to have 3 heads out of 10. And if you compute this, you can verify the answer is going to be this one. Please do it in your calculator. Now the other one is at least 3 heads. Well, in this case, we can compute, notice, for the part B, we can compute the probability for 0 heads, one head, and 2 heads. Probability of 0 heads is the same as before. It's going to be almost the same. Combinations 10, but now choose 0. Combinations 10, choose 0, divided by 2 raised to the 10. Now, probability of 1 head is combinations 10, choose 1, divided by 2 raised to the 10. And probability of 2 heads. Probability of 2 heads is combinations 10, choose 2, divided by 2 raised to the 10. What am I doing here? All right, the question is, what is the probability of at least 3 heads? At least 3 heads, this can be interpreted as 3 heads or more. But so we can compute the probability for, as we did it here, for 3 heads, then the probability for 4 heads, 5 heads, 6 heads, 7 heads, and so on. But we can do something better. Notice the probability to observe 0 heads, 1 head, 2 heads, 3 heads, and so on up to 10 heads is going to be 1. I mean, what is the maximum amount of heads we can observe if we are tossing the coin 10 times? It has to be 10 heads. So if we compute the probability for 0, 1, and 2, I mean the ones after before 3, and subtract that from 1, we're going to have the answer. So in this case, the probability is equal to 1 minus this probability we computed here. Combinations 10 choose 0 divided by 2 raised to the 10 plus combinations 10 choose 1 divided by 2 raised to the 10 plus combinations 10 choose 2 divided by 2 raised to the 10. Yeah? I want to be more explicit about my reasoning. If I compute the probability for 0 heads, it's this one. And if I add it to the probability of 1 head, that is this one, I can do it so on, but I have to do it only up to 10 heads. But this number must be equal to 1. What is the probability we observe no heads, 1 head, 2 heads, 3 heads, 4 heads, and so on up to 10? It has to be 1. For sure, you're going to have no heads or at least 1 head. Then, here we have, what I'm doing here, what I want to compute here is the probability of three heads probability for heads and so on up to 10 heads because it says 3 heads or more. But this is equal only to 1 because of this minus the probability before to observe 3 heads, that is this one, and this one. 1 minus combinations 10 to 0 divided by 3 raised to 10 plus combinations 10 choose 1 divided by 2 raised to 10 plus combinations 10 choose 2 I'm sorry, divided by 2 raised to 10. And there you have. So this is the same as this, right? So computing your calculator these numbers, you can verify that the answer is this one here. Please verify that. These examples are from Webwork, so you're going to find these examples on Webwork, but maybe the numbers are going to change a little, but the reasoning should be the same. Other example. What is the probability that if 13 letters are typed, no letters are repeated? Well, here assume there are only, in English, 26 letters. So first, the probability is going to be, I have to make a quotient. In the bottom, I have to count the number of elements in the sample space, and what is going to be that? If I'm going to create, let's say that I could create letters by repeating all of them. So I have to consider the possibilities with the 26 letters. So in this case, it's going to be 26 for the first one, 26 for the second one, and so on. Up to I write down 26 13 times. So this is 26 raised to the 13. Now I have to count here in the top the ones that are not repeated. Out of the letters of 13, out of the words with 13 letters, in how many of them I don't have any repeated letter? But I can do this in the next way. 26 I have 26 for the first letter, but since they're not going to be repeated, the other one cannot, I mean, for the next one, I don't have 26 options. I have 26 minus 1 because I already put 1 in the first place. So it's going to be 25. For the third one, again, I already have chosen 2. So it's going to be 24, and so on. Until what? Until I have 13 letters. But this can be computed only by using what? If you remember this technique, this can be computed by using permutations. So this is essentially permutations of 26 letters, choose 13, and compute this quotient. If you do it, you can verify that the answer is this number. This quotient permutations of these numbers divided by 26 raised to the 13 is going to be this answer. Please verify that. Other example. It says 2 cards are drawn at random from a pack with a replacement. What is the probability both are aces? Well, first, the pack has 52 cards. And we have 4 aces as total. So here, the same, the probability. Again, well, in this case, notice I'm going to compute this probability by using something similar as I did before, like this one. If I have 4 aces, yeah, and 52 cards at the beginning, what are the probability? Let's say that I'm going to choose only 1 card. I mean, I want to focus only on 1 ace. In my first choice, I know I'm choosing 2, but let's say that I'm going to choose only 1. If I'm choosing only 1, what is the probability that I select an ace? Well, since I have 4 aces from 52 cards, the probability is 4 divided by 52, right? But of course, I'm choosing 2 cards. So the next choice is going to be what? How many options do I have to select here? Now I have remaining 51 cards, and how many aces? If I have chosen 1 ace in the first choice, I will have only 4 minus 1, that is 3. 4 times 3 divided by 52 times 51. And you can verify this one is going to be the answer. Please verify that. Now, why are we multiplying here? Well, because we're selecting 1 ace and then another ace. We're applying with these 2 numbers the multiplication principle. I think here we call that product principle or product rule, something like that. But the multiplication principle, when you're creating sequences, selecting from several choices, each choice has different numbers. How do you know how many sequences you can form? You have to multiply the number of outcomes in each possibility or options. Other example, a committee of 4 is chosen at random from a group of 6 women and 3 men. Find the probability that the committee contains at least 1 man. All right. First, I'm going to compute the probability that we select one man. I mean, no man. This is the reasoning here is very similar to the one where we computed this one here. What was this one? This one. This one. No, why? Uh, a committee of 4 is chosen at random from a group of 6 women and 3 men. Find the probability that the committee contains at least 1 man. All right, again, at least 1. Let's say that we have the probability of 1, but we want the probability of at least 1 man. So I have to add probability of 1 man, probability of 2 men, plus probability of 3 men. Probability of 1 man. Of 2 men. And this one, probability of 3 men. So I have to compute that. But notice the same as before. What is the probability that we have 1 man, 2 men, 3 men? I mean, 1 man, 2 men, 3 men, or no man at all? That probability is going to be 1. Probability of 1, I mean, probability of 0 man, plus the probability of 1 man, plus probability of 2, plus probability of 3, that has to be necessarily 1. Why? What is the probability we observe no man, or 1 man, or 2 men, or 3 men? Has to be for sure, has to be 1. But we want only this. So the same as before, if you solve for this one, you will see that the probability of 1 plus probability of 2 plus probability of 3 is only equal to 1 minus the probability of no man. The probability of no man can be computed in the next way. Probability of 0 man I have to use counting techniques. First, it has to be, I have to count in how many ways I can choose 4, because the total I'm going to choose is 4, out of 6 plus 3, that is 9. But it doesn't say that we have to care about the order, so it will assume that the order doesn't matter. So in this case, it's going to be combinations 9, choose 4. Because we have 6 plus 3 is 9, and we're choosing 4. Now, in how many of these 4 I'm selecting no man? Well, first, how many men do we have? We have 3, and I want to choose 0. Again, so I can compute this by using combinations 3 choose 0. In how many ways I can choose 0 man out of 3? This is responded by combinations 3 choose 0. But now, times, in how many ways I can choose women? If I'm choosing 0 man, but I'm choosing 4 in general, necessarily the remaining 4 must be women. But how many women do we have to choose from? We have 6 women. So in this case, combination, we have 6 women to choose, and we want the 4 to be women. So this is the answer. Combination 3 choose 0 times combination 6 choose 4 divided by this. So the answer for this exercise is going to be 1 minus combinations 3, choose 0, times combination 6, choose 4, and divided by combination 9, choose 4. If you compute this number, do it in your calculator, you can verify that the answer is going to be equal to this. Please verify that. Finally, one more example. It says April, Bill, Candace, and Bobby are to be seated at random in a row of 4 shares. What is the probability that April and Bobby will occupy the seats at the end of the row? So here, notice, let's say that we have here the 4 seats, 1, 2, 3, 4 seats. We want to have in these two fixed 2 persons. April and Bobby, they're going to be seated here, right, in these two. April and Bobby. In how many ways you can seat them here? Well, you can have, for this we have 2 options. For the remaining, you will have 1 option. So it's 2 times 1 is 2. Why this? What is the reasoning here? Again, let's say that by now that we have only 2 seats, and you have only April and Bobby. In how many different ways you can see them here? Well, let's say that you have 2 options for the first one, and for the rest one, you have only 2 minus 1 is only 1. The remaining guys, that they are Bill and Candace, in how many ways you can see them here in the first 2 seats? The same as before, I have 2 options for the first one because I have only 2, the same as I said before. Let's say by now that we have only these 2 seats. So I have 2 options because I have only Bill and Candice, and 1 option. So it's going to be 2 times 1. And if you multiply all of this, 2 times 2 is only 4. Now, I have to count in how many ways I can seat all of them in general. But this is simple, right? Ways to seat all of them. I have 1, 2, 3, 4 seats. So I have 4 options for the first seat. Then after that, 3 options. Then after that, 2 options. And then finally, 1 option. So apply multiplication principle. And you will have 4 times 3 times 2 times 1 is 12 times 2, 24. So 4. So the probability is 4 divided by 24. If you simplify this, we see the answer is 1/6. And you can verify that the answer is the same as this one here. 2, this is 4 times 3, 2 is 2 divided by 12. This is going to be 1/6. All right, I understand that some of the problems that you're going to be seeing here, we have to use counting techniques, and I understand they might be complicated for some of you. So do not hesitate. If you have any questions, you email and ask me anything. Remember, you can also use my office hours if you are in the campus, or you want to have a virtual meeting, please send me an email so we can arrange an appointment. But feel free to ask any question about the exercises that you're going to do. I understand that if this is the first time you're seeing this, counting techniques is not very simple, right? See you later.